Hello everyone, welcome back to this data science series. In this lecture, we are going to cover data science model evaluation. In the last video, we have covered about training the model, and in this video, we are gonna learn about data science model evaluation, like evaluating the training model which we have constructed, like whether it is accurate or can be worked upon or not. So let's get started. Introduction to model evaluation. Like, what exactly is model evaluation? It is the process of assessing the model's performance on unseen data, because we have constructed a training model set. So we have to evaluate it first, that whether it can be worked upon on unseen data or not. It also helps us to determine how well the model generalizes the new or real world situation. And also it is very important for understanding how reliable is our model and it can be trusted or not in decision making, because it is very important to be reliable on a model. Then let's have a look on importance of model evaluation. It is identifying model flaws, selecting the best model, and ensuring reliability and trust. These are important factors of model evaluation, because it can identify the model flaws, it can select the best models out of all created models, and it can ensure our reliability and trust, because it is the most important thing in in any model to rely upon it. But how can we evaluate the performance of this model? It can be either accuracy, precision, recall, or F1 score. Accuracy is the proportion of correctly classified instances. It is 1 minus error. Precision is how precise it is. It is the proportion of correctly predicted positive instances out of all instances predictive as positive. It is TP, like truly positive, upon true positive, like all values that are predicted to be positive. Then recall is the proportion of correctly positive instances out of all positive instances. Precision is out of all predictive, and recall is out of all actual positive. And F1 score is a harmonic mean of precision and recall, balancing both matrices. Let's have a look on Python codes of model evaluation. First, how can we perform model evaluation? It is measures how well trained model performs on unseen data. And common techniques, it uses confusion matrix. What exactly is confusion matrix? It have true positives, true negatives, false positives, and false negatives. But what are these values? How can we evaluate true or false? There can be a variable which can have been predictive as positive but is not actually positive. So it is referred to as false positive. Whether if it really is positive, it is referred to as true positive. Same goes for true negative and false negative. Also, the matrices as we discussed are accuracy, precision, recall, and F1 score. And to summarize the performance, here we have used ROC curve and AUC, which measures the classification performance across the thresholds. Let's have a look on this code where we have used ROC curve and AUC, imported the important packages, and then we have this data set. We are splitting the data into train and test sets as we have learned in previous lecture. Then training a random forest model again in the lecture of decision trees. Then we have predictions, where we are using predict function to predict the test. Then we are evaluating, like it is a model evaluation. Now let's run this code. See, the confusion matrix is printed. Here we have precision, recall, F1 score, and support. Accuracy, macro average, and weighted average for each values. And ROC, AUC score 2. Now let's have a look on another, which is accounting for unequal error cost. In some case, the cost of false positives and false negatives is not same. But how is it? Why? Let's, for example, take a fraud detection case. where a false negative may be more costly than a false positive. Because if we miss a fraudulent criminal, he can cause more fraud activities. But if we alleged normal or a person who is not actually involved in fraudulent activities, we can release him later. It is not causing much um, cause. It is not causing much harm. But if a fraud is spared, he will surely not spare many. So in this case, false negative will be more costly than false positive. So we have to account for unequal error cost. So for this, we can use custom weight set class weights to give more importance to minority or costly class, because that's our priority. So we can have this code where we have trained the class weights and we have made predictions, evaluation with confusion metrics, and this is how our output looks like. Let's have its theory. Like handling error cost can be cost sensitive learning. Example can be medical diagnosis, because if a false negative a person missing a disease, then it can more harm in him in future, like our fraudulent activities. Then we have cross validation techniques, which can be k-fold cross validation method, stratified k-fold method, and leave one out cross validation methods. In k-fold cross validation method, we are dividing the data into k folds and training on k minus 1 folds, and then we are evaluating the random remaining fold, that k minus 1, one fold is remaining, and then we are repeating this process for each and every fold. Like if one is selected, then each can be covered. And stratified k-fold is ensuring that each fold maintains the same class distribution as the original dataset, especially important for imbalanced datasets, because every dataset is not important to be balanced. So we are using stratified k-fold method, which will ensure that each fold maintains the same class distribution. Then we have leave one out cross validation, as the name suggests. We are leaving one data point for training and evaluates all the remaining points. It is suitable for small datasets. We can use these techniques according to our datasets and needs. Let's have a look on the Python code of adjusting decision thresholds. So in this, we have by default classified thresholds set to be for 0.5, and then the threshold can help us to control false positive and false negative rates. This is the code. We are importing the packages, then we have created a synthetic data set, then trained a classifier, then we got the predictive probabilities, and then we have plotted this ROC curve. What actually this looks like is this. Using this curve, we can find a true positive, false positive, true negative rates. Like this is the true positive rate, which is going higher, and this is false positive rate. So this curve will help us to understand those things more deeply. Now let's continue with our lecture on running to hyperparameter tuning. What is hyperparameter tuning and what it involves? It involves grid search, it involves random search, and it involves Bayesian optimization. And then we have bias variance trade-off, which have bias, variance, and trade-off as its component. But what actually these are? Bias is underfitting the model if it is too simple to capture the underlying patterns in the data, and variance is overfitting. Like these are two poles apart, bias and variance. And variance is the model too complex to learn the training data too well, leading to a poor generalization. Like underfitting is also not a good thing, and so is overfitting. So trade-off is the solution. It is finding the right balance between bias and variance to achieve the optimal model performance. This is it for this lecture. We'll meet in another lecture which will cover the topic of naive based classification. Thank you for attending this lecture. Till then, stay tuned.